So continuing on with conservation of energy, the total amount of energy of a system, an isolated system, stays constant. So if we have an isolated roller coaster, so we start off with potential energy at the top of the hill. As we roll down the hill, we lose height, we lose gravitational potential energy, and we speed up, we gain kinetic energy. And at the bottom of the hill, we've converted all of our energy into kinetic energy. And then as we roll back up the hill, that kinetic energy gets converted back into potential energy, et cetera, et cetera. So if there's no friction, it's just a conversion back and forth between potential energy and kinetic energy. So where is this roller coaster going to be moving the slowest? It's going to be moving the slowest at the top of the hill, where it has the most potential energy and the least kinetic energy. Okay, when is this car going to be moving the fastest? Well, at the bottom of the hill, where it has the most kinetic energy and the least potential energy. So because of this, every hill has to be can't be any higher than the first one. And as a matter of fact, every hill has to be a little bit lower than the first one, unless there's something to pump energy into the system. Because when I roll up to this hill, I'm going to run out of energy before I get to the top of it if it's taller than my first hill. So in the real world, you can't even go up as high as the first hill, because the longer that you roll, friction exerts a force on the roller coaster. It exerts a force, and while the roller coaster moves, so it does work on the roller coaster, and that work converts energy. The energy of friction, the work of friction gets converted to heat, and the atoms start jiggling faster and that sort of thing. So because of this, each hill has got to be a little bit lower than the previous one. Otherwise, the roller coaster runs out of available energy to get up that hill. So they must be, each one must be a little bit lower. So let's look at a question here. There's two red marbles. One I simply drop, and the other one slides down a frictionless incline. And the question is not which hits the ground first, but which is moving faster when they reach the ground. Okay, and I'm not asking when they come to a stop. Okay, this one is just before it reaches the ground. It hasn't come to a stop yet. Well, if they both start out with the same amount of GPE, okay, because they're the same height, okay, that means they're both going to have the same amount of kinetic energy just before they reach the ground, which means they're both going to be moving at exactly the same speed. So in this case, so A, B, or C same. It would be C the same. Okay, so we've got a ball, and I throw it up at 5 meters per second from my hand. How fast is it reaching? Does it reach my my hand when it comes back down? How fast is it moving again? Well, conservation of energy tells us, okay, if it's got 5 meters per second worth of kinetic energy when it leaves my hand, okay, let's say that's 10 joules, okay, at the very top, it's going to have 10 joules of gravitational potential energy. When it comes back down, it's going to have the same kinetic energy. It's moving at the same speed as when it left my hand, assuming it didn't lose any energy to friction, wind resistance, and that sort of thing. Okay. Here we've got two ramps, identical rocks or balls. One ramp is steeper, the other ramp is flatter. And the question is, compare the speeds of the rocks, the balls, when they reach the bottom of the ramp. Steeper one going to be moving faster. Is the shallower one going to be moving faster, or is it going to be the same? Well, you might say, well, the steeper one's going to be moving faster because it's steeper, so it's going to accelerate more quickly. Or you might say that the shallow one is going to be moving faster because the ball is going to be on the ramp accelerating longer. So maybe it's that one. Or if you're savvy, you would say it would be the same because they both start with the same amount of GPE, which means they're both going to start going to end with the same amount of kinetic energy. Okay, so let's work a problem. A bow is drawn back with a force of 320 newtons for a distance of a half a meter. How much work was done on the bow? How much elastic potential energy is stored in the bow? And then how fast will a 0.028 kilogram arrow leave the bow when shot? So the first one, easy peasy. How much work? That's force times distance. So 0.5 times 320 equals 160 joules. Okay, the second one, easy peasy too. How much elastic potential energy is stored? Well, work equals the change in energy. So if I do 160 joules of work drawing back the bow, I've stored 160 joules of elastic potential energy. And the next question is, how fast will an arrow leave the bow when shot? So what I'm going to do is say, all right, that the energy that's stored in the bow is going to become kinetic energy of the arrow. Okay, so that arrow is going to leave with 160 joules of energy. Now, realistically, not all of that energy is going to get transferred to the arrow. Some is going to get lost, but we're looking at ideal situations here. So that arrow has 160 joules of kinetic energy, which equals mv squared over 2. Okay, so 160, and we plug in our 0.028 for our m, and then multiply by 2, divide by 0.028, and then take the square root of the quantity, and you've solved it, and you get that the velocity would equal 107 meters per second, which would be pretty fast. That's moving pretty good. Okay, let's say two magnets are attracted to each other. I let them go, and they move and they slam into each other. What type of energy was, what form was when? Okay, so initially the magnets start off with some sort of magnetic potential energy. Okay, as they move towards each other, they lose that potential energy and it gets converted to kinetic energy. Okay, and then after they slam into each other, that collision converts that energy into heat, and so the energy is just converted into heat. So we can think of atoms as behaving a little bit like tiny magnets in a rough way. Okay, it takes energy to break apart, to pull them apart, and then when they form new bonds, when they get closer to each other, they convert heat. That energy gets converted to heat, and so the energy that's released from chemical bonds through chemical reactions, we're going to call chemical potential energy. And we're going to keep this simple. We're going to say it's the energy released through burning or digestion. So when you burn something or eat something, that energy is chemical potential energy. Okay. Other types of energy that we haven't covered, we're not going to spend too much time on. Sound energy. Sound's a type of energy. Light is a type of energy. Electricity is a type of energy. There's nuclear energy. Okay, and there's any number of more types of energy that we could think about, but these are just the ones that we're gonna go with. So let's look at the energy conversions when you go for a ride in a car. So initially, the energy for your car starts in the form of gasoline, which you're gonna burn, which is potential energy, chemical potential energy. If you burn it or eat it, it's chemical potential energy. And then what form of energy does that chemical energy get converted to? Well, the car gets moving, so we gain some kinetic energy. Okay, some of that energy comes out the tailpipe as heat, so we lose some as heat for sure. Some of that energy gets converted to sound. I can hear that car. Okay, and some of the energy gets converted into electricity through a little generator in your car called the alternator. Okay, and that electricity gets converted into other forms of energy. It powers the stereo, so that the electrical energy becomes sound energy. It powers the fans that blow the air, so that gets converted into kinetic energy. Powers the windshield wipers, which is kinetic energy, and it powers your headlights, which is light energy. And we didn't mention lights. Light's a form of energy too. So, and then after you come to a stop, pretty much all that energy gets converted into heat energy. But anyway, that's just a simple example of going for a ride in your car. All of these energies are all getting converted into other types. Let's say you pick up a book. Let's say it's a physics book. If you haven't done that before, just pretend. Okay, where did you get the energy? If you pick up a book, you do work on it. Where'd you get the energy to do work on that book? Well, from the food you eat. Okay, and what kind of energy is that? It's chemical potential energy. Okay, and where did that energy get its food from? Where did the food get its energy from? Okay, well, it all starts out in the sun. Okay, and the sun is a great big nuclear reactor. Okay, so it smashes hydrogen atoms into helium atoms. So we start off with nuclear energy. That energy gets converted into light energy, okay, which travels to the Earth and warms up some of the Earth directly. So we've got some light, okay, and warms up the Earth. Some of that light energy is absorbed by plants. Okay, let's say we're looking at a corn plant. So that corn plant grows. So the light energy gets converted into what type of energy is going to be stored in the corn. Okay. Well, you might say gravitational potential since the ears got elevated, but that's not the one I was looking for. I was thinking of chemical energy. Okay. So that corn has got stored energy that we can eat. Okay. And then that gets converted in, that's kinetic energy. And then we eat it and we convert that into all kinds of forms. We convert it into heat. We maintain our body temperature. We move. So that energy gets converted into kinetic energy. Okay. If we eat more food than we use energy, we store some of that energy as fat, which is back to chemical energy. Okay. But all that energy starts out with nuclear reaction in the sun. The energy that you have to move and do anything and talk and pick up your phone and do whatever all came from a couple of atoms being smashed in the sun millions of miles away. So think about that. Okay. That is that for the notes for the unit. We'll have a test before too long. See the modules for the whereabouts of that or whenabouts. And good luck on worksheet 6.5.